Hi, my name is Art Porter. I'm with Agilent Technologies here at Colorado Springs, Colorado. I work in the High Performance Real-Time Oscilloscopes Marketing Group. If you're considering buying a wideband real-time oscilloscope, and by that I mean something with double-digit bandwidth, gigahertz bandwidth, double-digit gigahertz sampling rate, you're probably going to be working on some critical high-speed, low-amplitude signals that you really care about knowing the truth about them. In that context, one of the most important parameters to think about in purchasing an oscilloscope is noise. Because if the scope has excess noise, that eats up some of the margin in your design, both for amplitude and for jitter. Now, in real-time scopes, especially wideband real-time scopes, noise is a particular concern. Why is that? It's because you have a very wide bandwidth, and noise is typically 1 over f, so the more bandwidth you have, the more noise you have. Also, because we're sampling at a very high speed and the A to D converter has to run at those high speeds, that is a particular design challenge for A to D converters. So what I'm going to show you today is some ways that you can evaluate noise by doing some simple measurements that you can make on a wideband scope that you're considering purchasing or using. And I'll also show you some ways to most effectively use your scope and probe to minimize the effects of noise in your measurements. Let's first look at 3 different ways of measuring noise and looking at noise on the instrument. First, we can use the instrument's own automatic measurements to measure noise. So I've set up a AC volts RMS measurement here, and as you can see indicated in the measurement panel on the screen, we're measuring about close to 400 microvolts of RMS noise. Yeah, this is on our 13 gigahertz, 40 gigasample per second oscilloscope. To get a more statistical view of the noise, we can also use the built-in histogram function in the instrument. So here we've turned on a histogram. A little hard to see, it's a blue histogram on top of a yellow trace, but you can see it there. And we can look at the statistics of the measurement in the histogram panel at the bottom. And we can see that the standard deviation, which should be about the same as the RMS voltage we measured earlier, in fact we're measuring about 404 microvolts there. So this also shows us the min, max, and standard deviation and so on within that histogram. In addition to the statistical domain, we can also examine noise in the spectral domain, or in the frequency domain. So this instrument has a built-in FFT, and we can use that to look at the noise. And you'll notice that a large component of the noise is this broad band, what we would call white noise, thermal noise, which as you'd expect is fairly constant across frequency. Here's the bandwidth of the scope out here at around 13 gigahertz. The noise starts to roll off there. You'll notice there's also another component there. You'll notice these little spikes that stick up out of the broadband noise. Those are the effects of the digitizing on the scope. It's just the interleaving of the various digitizers that are used and the imperfections in those digitizers. So both of these contribute to the overall noise number. The energy in these narrow spikes is quite small because they're so narrow in frequency, so they don't contribute much to the total noise that we saw in our ACRMS noise measurement or in the histogram. That's why the histogram looked very Gaussian. But they are important. This broadband noise, which is uncorrelated, can be removed by averaging. These little spurs here cannot be removed by averaging because they are correlated. They're always at the same frequency. What really matters, of course, is signal-to-noise ratio. So to look at that, I have inserted a 1.1 gigahertz full scale, that is 8 division peak-to-peak signal into the channel. And now looking at the FFT again, you can see that spur right there, which is the 1.1 gigahertz input. We can put a marker on that, so then we can measure dB ratios for the noise and for the digitizing spikes. This will also allow us to look at a third component of unwanted or spurious information, and that is the harmonic distortion in the scope. So now I've placed a cursor on the top of the broadband noise, and as you can see here, the delta on the cursors is about minus 69 dB. So that means that this noise is approximately 70 dB below the full-scale signal. Now we can move that cursor up and look at the range on these digitizing spikes, and you see those range from about minus 60 dB to about minus 50 dB in that range. Now the spike right here at 2.2 gigahertz is the first harmonic of our 1.1 gigahertz tone, which is coming into the scope. So that is the dominant portion of the harmonic distortion. So let's measure that again using the cursor, and you can see that that is about 37 dB down from the fundamental at 1.1 gigahertz. So this is a very valuable test you want to make on your scope. Now, as we saw in that previous shot of the fast Fourier transform or spectrum, you can see that the noise is spread out all across from DC to 13 gigahertz. So one strategy you can use to reduce the impact of noise on your measurement, if you can live with lower bandwidth in a measurement, is to just reduce the bandwidth. The oscilloscope gives you a way to do that. So if we go from 13 gigahertz, where we were at 400 microvolts, down to 6 gigahertz, you can see you don't quite cut the noise in half, but pretty close. We're down to 230 microvolts there. So far, all the measurements we looked at and all the results we looked at were with the scope in its most sensitive range. So we were just looking at the native noise of the amplifier input stage of the scope. Now when you go to less sensitive ranges, the scope inserts an attenuator in here so that the scope now can get the correct scaling for larger amplitude signals out here at the front panel B and C connector. So if you insert an attenuator, let's say a 10-to-1 attenuator, the scope will think that this 400 microvolts noise here is actually 4 millivolts noise here at reference to the input B and C. So as you go up in the sensitivity ranges, you'll see that the measured noise does apparently increase, but our overall signal to noise ratio, of course, doesn't change. So the examples that we showed for the full screen signal to the noise will remain the same. So as we can see in this table here, as we change the volts per division from 5 millivolts up to 1 volt, the noise increases more or less in proportion as you would expect as we change the sensitivity. So to illustrate, as I change the sensitivity, go up to say 100 millivolts per division, on the scope you can see that we're now measuring 2.5 millivolts RMS, not 400 microvolts RMS. Another significant contributor of noise is a probe. If you're using a probe as opposed to using just a coaxial RF type connection. And it turns out the probe noise dominates for almost all measurements. We can see that here by looking at the measurements with the probe attached. We can see the probe is adding about 2.5 millivolts RMS to the overall noise, and as we go up in sensitivity, once again that noise from the probe also is increased. So to illustrate, now we've added a probe, and as you can see the noise is now measuring a little bit over 3 millivolts RMS. That is the combined effect of the probe's noise and the scope's noise. The key to this very low noise performance in these oscilloscopes is this proprietary patented Faraday shielding technology, which was originally developed for Agilent's high-frequency microwave instruments to achieve very low noise floors. So embedded in that, we've got the entire front end of the oscilloscope. So in this demonstration, we have shown that the Agilent oscilloscopes have the lowest noise of any equivalent wideband oscilloscopes in the market and the lowest noise in these wideband probes. We've shown how important noise is for you as a parameter to consider when selecting an oscilloscope. We've also shown you some ways that you can evaluate noise in any oscilloscope you're planning to purchase, and some ways that you can minimize the impact of noise in your measurements. Thank you.